I want to share with you one worked out example problem that will illustrate the analysis of a nozzle and how to determine nozzle efficiency. And what I'm going to do, the example is going to be based on this. This is just a basic compressed air nozzle that's used for shop floor cleanup or workshop cleanup. And some of you may have had some experience with a compressed air nozzle like this. So a supply of compressed air comes in here, okay? And of course the exit is here, and we simply press this open close valve down to get the air flowing. Now, let's see, I'm going to look on this. Yes, here it says right here on the wording of this nozzle, it says 150 PSI maximum inlet pressure. And so this is designed for a maximum of 150 PSI. Typically, for example, in my workshop, I use air that's held at 100 PSI. And then there's plenty of compressed air to go around. So we're going to do an example problem that's based on this piece of equipment here. And in previous example problems, previous homework problems, I think in some of my online sessions, I have shown you a couple of nozzles here. This is a Sidewinder missile nozzle, and this is a Hellfire missile nozzle. And you'll notice a difference between these two and this compressed air nozzle. So that compressed air nozzle, very similar to this one. Notice here how on the compressed air nozzle, notice how this nozzle end is a converging shape. It starts at a maximum diameter and necks down to a smaller diameter. Let's look at these. Now, these are rocket engines, and here's the inlet of the Hellfire missile rocket engine. And notice how it's got a certain inlet area, and the cutaway view here shows that it's converging and then diverging. This is called a converging diverging nozzle. This one is called a converging nozzle. Now, the reason that these rocket engines are converging and diverging, now do notice here that even with these, the outlet area is smaller than the inlet area, but they're designed to be converging, diverging in order to achieve supersonic flow at the outlet. Supersonic flow, in other words, faster even than the speed of sound. So now this industrial air nozzle, converging only, it's designed to have an exit velocity that's below sonic velocity for a lot of good safety reasons, correct? And so this converging nozzle is designed to only to only deliver subsonic velocities. All right, so with that detail, let's continue on. What I want to cover is just the basic governing equations for nozzle calculations. And then we'll do an example problem to illustrate how will you calculate the mass flow of this nozzle. We'll apply the first law to determine the outlet velocity. And then we'll do the traditional, what's the nozzle efficiency of this piece of equipment. So let's do some basics first, basic reviews of fundamentals. Okay, let's start with a sketch. And so do you see that for my compressed air supply nozzle, it's converging. So I'm trying to show in my sketch a converging nozzle. Here's my control surface. I've got one inlet, one outlet. I'm showing m dot coming in. It's going to be steady state, steady flow, isn't it? Another thing is we model these nozzles as fully insulated, so there's not going to be any heat transfer from a traditional nozzle, no heat transfer. And just from the sketch and just from looking at this piece of equipment, is this lifting a weight? Is there a shaft protruding from this piece of equipment? Can we detect work? And the answer is no, there's no work being done. W dot over m dot is 0. So we'll just write down little w out equals 0. So steady state, steady flow, one inlet, one outlet. Let's write the continuity equation. M dot equals rho 1A1 V1. Rho is the density, and that exactly equals rho 2 A2 V2. Statement of continuity. We're going to use that. Let's look at a statement for the first law. Steady state, steady flow. Well, Q in, 0, insulated, minus W out, 0, not lifting a weight. So 0 equals H2 minus H1, enthalpy change, plus 1/2 V2 squared minus V1 squared, kinetic energy change. And so in general, the way to think about nozzle flows, given a fully insulated nozzle, do you see that there's an interchange between enthalpy change and kinetic energy change? The sum of those two has to add up to 0. Enthalpy change, kinetic energy change. Now, second law, if the nozzle flow is reversible and adiabatic, if the flow inside this converging nozzle, if it is reversible, no unrestrained expansion, okay, then S2I equals S1. That's if it's reversible. Now we know it's adiabatic. If it's reversible, S2I equals S1. And so then we define the nozzle efficiency. Nozzle efficiency, we're going to go to your book, is defined as the actual kinetic energy leaving the nozzle, the actual kinetic energy leaving, 1/2 V2 squared, divided by the isentropic kinetic energy, 1/2 V2 isentropic squared. And here's the screenshot from your textbook, section 612.2, defining nozzle efficiency. So do you see, this would be the actual kinetic energy leaving the nozzle divided by the isentropic kinetic energy leaving the nozzle. And so I'm going to bet that you're starting to see the drill now. You're starting to see the repetition of the way we study these processes. Is we're going to first study the isentropic process, and then we're going to determine the nozzle efficiency using the actual process that we observe. So here's our example problem. And what I want to do here is say we're going to have air, we're going to have compressed air. And look, for this type of fairly typical industrial application, we're going to model our ideal gas as having constant specific heat. Constant specific heat. Okay, so here's our problem. Compressed air at, I'm going to have to move my zoom, here it is, 600 kPa and 27 degrees C is coming enters a fully insulated nozzle. 600 kPa, so that's 6 atmospheres, okay, and 27 degrees C is entering the nozzle, okay, with a velocity of 9 meters per second. 9 meters per second. So we know the velocity coming in. The inlet diameter, now I've gone ahead and I have measured the inlet diameter of this nozzle. There's the inlet diameter. It's 3 millimeters. And then I've gone in and I've measured the outlet diameter. Now it looks probably, you might be able to see this and you might not, but it is a tiny little hole, and I have measured that tiny little hole to be 1.5 millimeters diameter. Okay. The actual air temperature at the outlet of the nozzle, we've put a thermocouple in here and measured it to be 0 degrees C. Pretty cold, 0 degrees C, cold air. And the outlet pressure is 100 kPa. In other words, about atmospheric pressure. What do we want to, here's what we need to determine. The mass flow rate of air. We have enough information to determine the mass flow rate of air. We want to determine the air exit velocity. And then finally, we will determine the nozzle efficiency given our field measurements. Okay. We want to model the air as an ideal gas with constant specific heat. All right, so let's start with a sketch. Pretty simple sketch, isn't it? No moving parts, no heat transfer, no work. Okay, so we're showing the inlet conditions, the inlet diameter, the outlet conditions, the outlet diameter, and we're going to write down M dot is rho 1A1 V1. Let's see, what do we have here. Oh, I didn't write down on my sketch that we have V1. We have velocity at state 1. Okay. Do we have A1? Yeah. Okay, we have the inlet diameter. It's easy to calculate A1. How will we get rho 1? How will we get the density at state 1? Let's think about it. How will we get the density given this information? We have an ideal gas. We have pressure and temperature. We'll use the ideal gas equation of state. Rho equals P over RT. Rho equals P over RT. That's the ideal gas equation of state. Okay, let's draw a TS diagram looking ahead in our analysis. So here's our inlet state at 600 kPa. Okay. Outlet state, a lower pressure, 1/6 at 100 kPa. Say, well, where's that vapor dome? Well, the vapor dome for an ideal gas is way down here. So for our TS diagram, we're way over to the right compared to a vapor dome. We're in the ideal gas region. Okay, so we've got process 1 to 2 isentropic. We'll study that first, study the isentropic process, but we know we don't have an isentropic process. It's adiabatic, but there's going to be some irreversibilities here due to unrestrained expansion. And so we're going to show a dashed line coming up to state 2A, and we've measured the temperature with a thermocouple. It's 0 degrees C. It's cold. And so I'm going to expect T2I to be even colder than 0 degrees C just by looking at the TS diagram. Okay, so here, before we put pencil to paper, here's what we're going to do. Might as well just get the inlet and outlet areas in square meters. We'll just calculate that. We're going to use the ideal gas equation of state. PV, P times little v is equal to RT, or rho equals P over RT, either of those, okay, to determine the density rho at the inlet and the outlet, because we know the actual outlet temperature. We measured it. So we're going to determine both of those values for rho. Then let's see, at the inlet state, we've got rho, we've got the area, we've got the velocity given, so we'll determine the mass flow rate. Once we have the mass flow rate, we can back solve at the exit to find the actual outlet velocity. We'll have rho outlet, A outlet, we have m dot, so we'll back calculate V2 actual. Then we will study the isentropic nozzle flow. Now, for an ideal gas with constant specific heat, we're going to remember something. This is something we should remember if you've used it enough, okay? Otherwise, it'll be formula sheet material, but with the special case, PV to the K is constant for an ideal gas, constant specific heat, undergoing a reversible adiabatic or isentropic process. PV to the K is constant. We're going to be able to solve for T2 isentropic. Once we've got T2 isentropic, we'll use the first law for the isentropic process to determine V2I, V2 isentropic velocity, and then a straight use of the definition of nozzle efficiency, the kinetic energy actual, V2 actual squared, divided by the kinetic energy isentropic. That's going to be V2 isentropic squared. All right, so we'll move ahead. Let's get CP and K and R for air. At the inlet conditions, 300 degrees C. All right. And so we're going to look it up. We're going to write down, we're going to write down K as 1.4. We're going to write down, we can write down C sub P, 1.005. And where did I get R from? There's two ways to get R. One is R bar over the molecular weight. That's going to work if you want to do it that way. Or you remember the identity for an ideal gas, Cp minus Cv is equal to R. So you can take 1.005 minus 0.718 to also to get 0.287. That's R for air. All right, let's determine the inlet and outlet areas. Pretty straightforward here. We know the inlet diameters in millimeters. We'll switch those into meters. And then we've got an area of pi over 4d squared. So here are our little tiny areas. 7 times 10 to the minus 6 square meters at the inlet, and even less, 1.77 square meters at the exit. Tiny square meters. All right, now let's go for the densities. PV is equal to RT, and so you should be able to quickly derive. You only need to write one of these down on your formula sheet if you're allowed to have those. But we're going to use rho is equal to P over RT. That's a perfectly valid statement of the ideal gas equation of state, okay? We'll stay in kPa to get our units correct. We need to transform our temperatures into absolute temperatures. We'll add 273 to our degree C. And then straight plug and chug, rho 1 is 6.97 kilograms per cubic meter, and rho 2, lower density, 1.28 kilograms per cubic meter. Pretty straightforward. So we got our rho values. All right. Well, let's go find our mass flow rate at the inlet. M dot is rho 1 A1 V1. Okay. So here's V1. Okay. So here's M dot, rho 1. We just found it. A1, we just found it, times V1, 9 meters per second. So M dot is 4.4 times 10 to the minus 4th kilograms per second, a small number. Well, that makes sense. You're not going to get a lot of kilograms per second coming out of this tiny little hole. Okay. All right. And so then what's the next step? Find V2. So that we're third through the problem. The mass flow rate is 4.4 times 10 to the minus 4th. Then quickly, we're going to be able to determine the outlet actual velocity. M dot is rho AV, so we'll solve for V2 as M dot over rho 2 A2. Here we go. All right. So the actual outlet velocity, 197 meters per second. M dot over rho 2 A2, 197 meters per second. That's fast. Look at our inlet velocity, 9 meters per second. Same mass flow rate, 197 meters per second. That's moving. That's going to clear a lot of material away. When you open this valve up, there's going to be a lot of material moving along. The next thing we're going to do is do our isentropic analysis. So we need to study this isentropic process. Do you see that we just finished sort of analyzing this irreversible process because we had T2 actual, it was given to us. We measured it in the field. Okay. So we've already analyzed that. Now we're going to go and analyze the isentropic process. And for an ideal gas with constant specific heat, P1 V1 to the K equals P2 V2 to the K. And we're trying to find T2 isentropic. Well, I don't see T2 isentropic here. Oh, but we can solve for it because we know the ideal gas equation of state. V is RT over P. And so I'm going to substitute RT over P for little v. All right. And so now I'm not going to drag you through the algebra of this relationship, but here's where we started. P1 V1 to the K is P2 V2 to the K. And as long as you're satisfactory in algebra, you can show that T2 isentropic is equal to T1 times P2 over P1 quantity to the K minus 1 over K. All right. And so you could consider that a formula that you may wish to put on your formula sheet. I would suggest that you just get good enough to derive it on your own, but you might put this on your formula sheet, but by golly, next to it, you've got to have ideal gas, constant specific heat, that's K is constant, and isentropic process, reversible adiabatic. So if you want to put this on your formula sheet, go for it. You've got to have some words next to the formula. Okay, so with that, and so in my work, I like to go ahead and compute the quantity K minus 1 over K. K is 1.4. And so K minus 1 over K is 0.286. All right. So I've got that little intermediate work here. That's my exponent. And so then it becomes easy to solve for T2I, 179.8 degrees K. So when I subtract 273 from that, I get a really, really cold outlet temperature, negative 93. So look at this. Negative 93 would be considered the isentropic outlet temperature compared to the actual measured temperature of 0 degrees C. Wow, it's a pretty big difference. So that means there's some irreversibilities going on in this piece of equipment, some unrestrained expansion going on within this piece of equipment. And that certainly is true. A lot of unrestrained expansion. Okay, so we found T2I. Remember what we're driving at. We're trying to find the isentropic velocity at state 2. All right, so we're going to write down the first law. So we're still studying process 1 to 2I. Let's write the first law down. Q in minus W out. Both of those are 0, equals 0, equals enthalpy change plus kinetic energy change. Now, this is something that, of course, Q in minus W out. If you're going to go formula sheet, you've got to have this left in. You can't just put 0 equals blah, 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 and then you'd have to write a paragraph out on what it applies to. But with the statement of the first law and the definition of constant specific heat for an ideal gas, let's see the next step. We've got 0 equals change in enthalpy for an ideal gas with constant specific heat is simply Cp times T2I minus T1. Delta H is equal to Cp times delta T for an ideal gas with constant specific heat. Cp is a constant number, okay? Plus 1/2, then the kinetic energy change, 1/2 V2I squared minus V1. So we're down to one equation and one unknown. Everything is known except for V2I. We need to remember in the back of our minds a units conversion. Okay, I can chase you back to other PowerPoints where you convert 1 kilojoule per kilogram is equivalent to 1,000 meters squared per second squared. And that's how we got this 2,000 term over in here. Instead of just 1/2, we've got 2,000. Okay, so we're solving for V2I. So that's how I got the 2 to come over to the to that. And yeah, 2,000. There we go. And so it does look. Here we go. And so in doing my work, I am seeing. So I say, gosh, in my PowerPoint, I didn't drag out the C sub P term. Well, it looks like I did here in my solution. H2I minus H1 is Cp times T2I minus T1. It's minus 120.8 kilojoules per kilogram. So I solved for the enthalpy change straight out, minus 120. Temperature's going down. Enthalpy is decreasing. Makes sense, okay? So then I'm going to solve. I'll solve for V2I, the square root of V2 squared minus 2,000 times the enthalpy change. So I've got V2 isentropic is 491.6 meters per second. That's really, really fast. Well, but that's not what we have, is it? We have an actual velocity that we just calculated a few slides ago. What we're driving at is nozzle efficiency. That's why we got nozzle efficiency. And so the kinetic energy actual divided by kinetic energy isentropic, all I need to do is write down the velocities, right? And then remember that kinetic energy is in terms of V squared. Okay, so let's see. Kinetic energy actual is going to be 196.6 squared divided by 491.6 squared, okay? And that's how we're going to come up with a nozzle efficiency of only 16%. Now, this is very realistic. So this type of nozzle that's used for industrial cleanup, blowing compressed air around for cleanup purposes, nozzle efficiency, very low, but it gets the job done. Okay, so and so this is dramatically different than building a rocket, right? So this piece of equipment here probably cost, I'm going to guess I paid less than $10 for this. Now, that was a few years ago, so I'm sure it's a little more expensive now, maybe a lot more expensive, but this is just a $10 piece of equipment. What did we just do? We determine the mass flow rate if we need to. There can be some cases where we have enough data where we don't even need to calculate the mass flow. We determine the actual outlet properties. We had to do that in the field, make some field measurements. Okay. We're going to compare the actual properties to the isentropic process. And then that's going to be enough to determine the nozzle efficiency. So there you go. That's what we've got. Just one worked out example for a nozzle. I hope, and so now that we've got a little bigger view, I'm going to try to see if I can bring this closer to the camera. It doesn't look like it's working. Darn it. I was hoping that you could see the tiny little nozzle area, but it didn't look like it was visible. Okay, I hope that helps. I hope that helps with your understanding of how nozzles work and how to do nozzle calculations, particularly nozzle efficiency. And for those of you interested in supersonic flow related to the rocket nozzles, there is an upper level mechanical engineering course. In my time, it was called compressible fluid flow. It's also called fluid dynamics. And I'm not sure if that technical elective is still offered, but if you have a great interest in supersonic flow, check with your undergraduate advisor or a faculty member in thermodynamics, and they could give you some guidance on that. So hope you enjoyed it, and good luck with your computations.